All righty, good morning, everyone. So just a reminder, we talked about yesterday. So we talked about force on a current carrying wire in an external magnetic field. So here we said the most general thing, which includes the fact that the wire could be curved and that the magnetic field could be in general non-uniform, so meaning it's not constant. In that case, the magnetic field on the wire is on the integral of the current integrated along a differential length, where that differential length is along the wire itself, crossed then by the external magnetic field, or in the case that it's a straight wire with a constant magnetic field. In that case, this thing simplifies then to the current crossed by the length, crossed by the magnetic field. And again, just to define these things. So again, here's my straight wire, and the current running in some direction, and we run it this way this time. Great. So in this case, we define a length vector, L, which then points in the direction of the current, but the magnitude of that is simply equal to the length of the wire itself. And the magnetic field is going to point off in some direction. So this is my magnetic field. So if I wrote this in terms of the magnitude, I would then define this angle of theta here, which is then the angle between the current and the magnetic field. So that the magnitude of the force then would be equal to the current times the length times B, all times. Go. Current times the length times B times sine of the angle between the two. Or again, this angle is specifically the angle between technically the length vector and the magnetic field. But again, since current is in the direction of the length vector, or of the current, I should say, then that's the angle. Great. So we talked about the right-hand rule yesterday. So there's one other thing I want to talk about with cross products, which is the more general way to do cross products instead of just relying directly on the right-hand rule, because sometimes the right-hand rule doesn't, I don't want to say it doesn't work, but sometimes this thing here is actually very, very difficult to calculate, especially if I give you a three-dimensional scenario. So let's look at a cross product then in general, which is a three-dimensional scenario, and how we actually calculate this guy. We're going to use it as an example here in a second. But anyways, let's say I have my three vectors. So A is equal to AX in the I-hat direction, plus AY in the J-hat direction, plus AZ in the K-hat direction. And then B and C are follow suit. So what I want to calculate in this case then is what is A cross B, and then from that, extract the components of vector C. Okay. So for those of you in Calc 3, of course, this is what you saw in the beginning of the semester, but the rest of you, we did talk about this in 205, so we saw this once, but let's kind of refresh our memories. So the way this works is we set up a matrix, and then we're going to take the determinant of this matrix. Okay. So this is going to be a 3x3 matrix, where the first row of this matrix is simply the directional property. So here I'm going to have an I-hat, a J-hat, and a K-hat. And then my second two rows are then going to be the components of A and then the components of B. So along this row, I'm going to put the components of A. Along this row, I'm going to put the components of B. So this thing is going to become then what's AX, AY, AZ. And then this is going to become BX, BY, and then BZ. So from here, we then have to take our determinants of our matrix. So that's what these straight bars mean. So these straight bars mean that we're taking the determinants. So the way this works is you first look at the first component. So here's my first component. Okay. And we're basically going to cross out then the row and the column below this guy, but then multiply everything by that component, which this component then is that first component of I. From here, we're then going to take what's known as the minor, or the matrix of the minor, the determinant of the minor matrix there, if I could actually speak, which is then going to be this guy times this guy minus this guy times this guy. Okay, so this first component then is going to be equal to AY minus then, or times BZ, minus then BY times AZ. So this is my first component of my results. Great. From there, we now go to the next component. So in this case, again, I'm going to cross off the first column and now the first row and second column, and now multiply everything by this guy. Now this one actually gets a negative sign put out in front, so I'm going to get a negative J-hat, and I'm going to do the same thing. I'm going to multiply this by the determinant of the minor matrix, which means I'm going to multiply this guy times this guy minus this guy times this guy. So that can be equal to then AXBZ minus then AZ times BX. This is my second component. Finally, for the last components, do the same thing. I'm going to cross off the first row, and now this time the third column, and then keep this element here. So everything's going to be multiplied by k up front. And then finally, I'm going to take my determinant of my new minor matrix, which is now this one. So I'm going to take this guy times this guy minus this guy times this guy. So finally, I'm going to get an ax by minus then a y times bx. So this is my cross product. So this is in general what the cross product is. So whenever I have three-dimensional vectors, this is the way I would actually have to determine the matrix. Now, what I know though in general, again, is that A cross B is equal to C, which means that since this is equal to C, this thing then has to be the x component of C, this has to be the y component of C, and then finally this has to be the Z component of C, because I know C looks just like this, right? So here I'm just translating or reading off what this thing happens to be. So from here I can then say, well, my x component of C then is going to be equal to, according to this, AY times BZ minus then AZ times BY. So this is my x component. My y component from here, I'm going to distribute the negative sign on each side. So we're going to make this guy positive, this guy negative. So this is then going to be equal to AZBX minus then AXBZ. And then finally, my z component then is going to be equal to, from this guy, simply then the AXBY, and etc. So it's going to be AXBY minus then AYBX. So these are then the components of my product. So this is the components of the product, which is generated by these two other vectors. Now, the point of going through all this, of course, is that if you don't know how to do the determinant of a matrix, don't worry about it. Here are the components. Make sure these things show up on your equation card, and that's all you care about. But again, we'll use this in a second. What's up, Omar?
What is the negative j? Where's the negative j hat?
Oh, the negative j hat was, so again, I'm looking at the components, which means I don't care about the I hat, the j hat, the k hat, because this is the cx component, this is the cy component, this is the cz component. But here I brought the negative sign on the inside, which is why this term comes before this term. So that's where that negative sign comes. Okay. Now there are reasons that negative sign shows up on there, but I'm not going to explain those. So like, just note it's a has. So let's put all this stuff together. Let's do a couple of examples, and then we use a cross product example here in a second. But my first example says that restart. Great. So here's my first example. This says we have a rectangular loop of wire hangs vertically in an external magnetic field. A uniform external magnetic field is directed horizontally, perpendicular to the wire, and points towards you at all points. Okay. So let's start drawing what this thing is saying. So what this says is I have a wire. So here's my wire. It's a rectangular shape of wire. And then I have a magnetic field, which is pointing perpendicular to that at you, which means our magnetic field looks like this. So in this case, our magnetic field points outward. And we're told it's uniform, i.e. constant. Those are our magnetic field. Great. And remember, those dots just mean it's going out. Then it says, in a portion of the wire that is L is equal to 10 centimeters long, a downward force is determined to have a magnitude of F equals to 3.48 times 10 to the minus 2 newtons when wire carries a current of 0.25 amps. Okay, so let's draw what that means. So that means that, let's say this is the section we're looking at, which is this part. So we're told L here is equal to 10 centimeters. This thing then has a force which is downward on it. So this is the direction of force, F of B, where the magnitude of F of B was equal to, down 3.48 times 10 to the minus 2 newtons. And we're told that it has a current running through it where that current is equal to 0.245 amps. So this is how much current is running through the wire. So what it says then is, what is the direction of the current in the wire? And what is the magnitude of the magnetic field that this thing is in? So these are the things that we want to know. So first thing I want to know is, what is the direction of the current running through the wire? Meaning, is the current running in this direction or is it running in this direction? How do I know? And then from that, extract the magnitude of this magnetic field. Okay? So first things first, let's deal with the direction. So direction. So okay, just a reminder, we know that the magnetic force is equal to the current times the length crossed then by the external magnetic field. Now, typically, the way we work this is, as we talked about yesterday, we point our fingers in the direction of the first vector, which in this case would be in the direction of the current, cross then towards the external magnetic field to get our thumb to then point in the direction of the force. In this case, what we know is a little bit different, where we know the direction of the force, i.e. we know the direction our thumb points. We know it's being curled to, which is B, which means we have to figure out what direction do we have to first point our fingers in to then establish our force to have to be downward. So from that, we then have to figure out the direction of the current. Okay? So first things first is we know what? Our thumb has to point downward. Now we know our magnetic field is that way, which means we want to curl our fingers in that direction, which means the only direction the current can be, which is the direction my fingers have to point initially, is the direction of the current. So which way is the current moving? To the right. Good. So in this case, we know that our current has to be running through the wire in this direction. So first thing is, the current must be going to the right. Which right-hand rule was that? That's right-hand rule number 2. Didn't you just use number 1? Well, number 1 only tells me the direction of the magnetic field created by the wire. Oh, that's not bad. Correct. So this is not created by the wire. This is an external magnetic field which it just put into. So that's the distinction between the two. So the first one is only the magnetic field created by the wire itself. Everyone's okay? From here, we can now just what? Figure out the magnitude of the magnetic field. So again, what do we know? We know that the magnitude of the force is equal to 3.48 times 10 to the minus 2 newtons, but that's also going to be equal to the current times the length times the magnetic field times sine and the angle between the two. Those are just our definition of the force. Now in this case, what we know is our current is moving that way, our magnetic field is moving that way. So what's the angle between these two vectors? 90 degrees, right? So in this case, we know the angle between the current and the magnetic field is simply equal to 90 degrees based off of our picture. And what's sine of 90 degrees? 1. So this is the same thing then as simply the current times the length times the magnetic field, which means the magnetic field then is going to be equal to the magnitude of the force divided by the current times the length.
So how did you figure the 90 degrees again?
Oh, so remember that angle is always the angle between, so you're right, check it back here. So this angle here is always the angle specifically between these two things, the two vectors. But this one always points in the direction of this one, so technically it's the angle between these two. So here I have to first establish what's the direction of the current. So again, we know the current is going that way. We're told in the problem that the magnetic field points that way. So now I'm just looking at the angle created by this. Okay. Plug my numbers. This then is going to be what? 3.48 times 10 to the minus 2 divided by the current, which is 0.245, times the length, which is 10 centimeters or 0.1 meters. Plug my numbers. What I find in this case then is this works out to be 1.42 joules. Or sorry, joules. Teslas. 1.42 Teslas. So that's the magnitude of our magnetic field. Okay? And in case you're wondering what a Tesla is, so this actually will establish what a Tesla is. So this has units of newtons, this has units of amps, this has units of meters. So it means this has to have then units of a Newton per meter per amp, which means a Tesla is actually Newton per meter per amp. So a Tesla actually a Newton per meter per amp. This is actually what a Tesla is. What's up?
What is a Tesla like? How strong is that?
Oh, that's a good question. So a single Tesla. Try to put it into context here. So scribbles out somewhere. So a Tesla is actually 10 to the 4 times the size of a Gauss, because a Gauss is 10 to the minus 4 Tesla. So let's see here. So your typical bar magnet that you put on your refrigerator, for example, is about a Gauss. Actually, sorry, about 100 Gausses. So well, that'll put it into context. So this was your refrigerator, and then you got a little bar magnet on here. So let's say the Statue of Liberty, that was New York. Right. So this thing has a magnetic field strength of about 100 Gauss. And again, 1 Gauss is equal to 10 to the minus 4 Tesla. So this is going to be about 0.01 Teslas. So it's about the size of a Tesla. So that means a Tesla itself would be equivalent to 100 bar magnets that you put on your fridge. What is the size of a Tesla?
So the other two magnets to the Gauss numbers add together.
Right, so if I put them on top of each other, as long as the magnetic fields are pointing in the same direction, then yes, then you would add the total magnetic field together. So yeah, so if I stacked a bunch of these guys basically on top of each other, so all the axes are say pointing in this direction with magnetic field, then this would then just be the sum over all of the individual magnets. Exactly. So we would just use the superposition principle that we looked at when we did electric fields. So, and again, as we know from lab, the Earth's magnetic field is only what, 5 times 10 to the minus 5 Teslas. So Earth's magnetic field is actually ridiculously, and it's getting smaller. Okay, get a better idea what a Tesla is. So a Tesla itself isn't overly powerful, but you know when you have a really strong magnetic field, you can get to high values of Teslas. Good. So let's do another example. So next one then says, there it is. So this one says that we have a rigid wire carrying a current of I that is clockwise around the loop, consists of a semicircular section of radius r and 2 straight portions. The wire lies in a plane perpendicular to a magnetic field, which in this case is uniform, that is into the board. Okay, so let's draw this entire scenario. So basically what I'm told is I have 2 straight wire sections. So here's straight wire section number 1, straight wire section number 2. And then I have a semicircular section, which is this guy, connecting these 2 pieces where this has a constant radius of r. We have currents moving in the clockwise direction, which means over here my current's going like this. So here I have currents going this way, here I have currents going this way, and then here I have current going this way. And then I'm told this is in an external magnetic field, where that next external magnetic field is pointing into the board or into the page in this case. So this is my magnetic field, and we're told that this magnetic field is simply uniform, so it's constant everywhere throughout space. Let's go back to our question. So this then says the straight portions each have a length of L within the magnetic field. Determine the net force on the wire due to the magnetic field. So we're told that this section here is the same as the other one, which is a length of L. Also a length of L. What I'm looking for then is what is the magnetic force on this wire? So what's the net magnetic force? Cool. So let's talk about these things. So first of all, this part here is a straight wire, which is carrying current in a uniform magnetic field, which means this one I can simply use the FB is equal to IL cross B. Same thing over here. This portion here, though, is a curved wire, which means it's not straight, but it's in a uniform magnetic field. But as long as it's not straight, that means I'm going to actually have to do the integral portion. Okay? So technically, the total amount of force on this wire then is going to be the force from this side, plus the force from this side, plus the force then on this semicircular piece. So let's write all that down. So in this case, I know the net force on this guy is going to be equal then to the force on the left wire, plus the force on the semicircle, plus then the force on the right wire. That is a little water in this case then. Okay? Now, let's go back. What else do I know? I also know that what? The force on this section of wire here is exactly the same as the force on this section of wire because the lengths of the wires are the same. Which means the magnitude of the force is exactly the same. The other thing I can do is I can establish by the right-hand rule that the force on this piece plus the force on this piece equals 0 because this force is equal and opposites of this force. What's the direction of the forces? Well, in this case, again, I would put my fingers in the direction of the current. Current is moving upward. Curl towards the external magnetic field, which is into the board. Curl in, which means the force on this piece is going to be to the left. So for this one, the force on the left one is to the left. On this one, again, I put my fingers in the direction of the current, which means I go downward, curl towards the external magnetic field, which again is into the board. My thumb then points in the direction of the force, which in this case would be to the right. So what happens in this case then is the force on the right plus the force on the left are equal and opposites, and they simply cancel. Okay with this? I know they cancel because the current here is the same as the current here. The length here is the same as the length here. The magnetic field here is the same as the magnetic field here, which means these two forces are equal and opposite, so they simply cancel. Okay? Good. So what that tells me then is that, well, this thing is simply going to be equal to the force on the semicircle. The other two portions are equal and opposite. Everything okay? What's up there?
So the direction of the magnetic force on the semicircle would point radially away.
Correct. But most of those pieces are going to cancel each other. We're talking about that in just a second. Good. So let's go from here. So what we know then is this guy's going to be equal to then the integral of the currents integrated over the differential length crossed then by the external magnetic field. Let's look at this guy. Good. So first, let's look at the direction of the force. So as Derek said, he's absolutely right, is the direction of the force on this guy is actually going to be in the radial direction. And I know that's because, again, I would use my right-hand rule. So in this case, I would take a section. So let's look at this section here. I'd point my fingers in the direction of the current, which in this case is moving here. Curl towards the external magnetic field, which means my thumb would point off in this direction. So at this little section here, my thumb then points this way. So this is the direction of the magnetic force on this piece. But now let's look at a symmetric piece over here. So at my symmetric piece over here, what's happening is the current is at this moment moving in this direction. That's the direction of my currents. So I put my thumb in, or fingers in the direction of the current, curl towards the external magnetic field. My thumb then would point off in this direction, which means that now my magnetic force on this portion is going to point this way. So exactly, what's happening then is that my force is basically doing this. Okay? But let's superimpose this force here on top of this force. What can you then tell me? The horizontal pieces are going to cancel, right? So not the vertical pieces, but only the horizontal pieces. So in this case, if I look at the vertical pieces, both vertical pieces are pointing in the same direction, but the horizontal pieces are equal and opposites, which means the total net force is only going to point in the upward direction. So in this case, my total force will only point this way. So it's going to be my total net force. Is it okay? So from here, let's establish a coordinate system. So let me call this my x-axis. And call this then my y-axis, so that the force itself is only going to point in the y direction. Let's call this my angle of theta. So in this case, actually, let me not call it theta, let me call it phi. Let me call it a different angle. Let's call this the angle phi. Again, this is our radius of arm. So here we need something in here that basically tells me that what this thing has to point only in the vertical direction. So which trig term is going to tell me my force only points in the radial direction or the vertical direction? Sine, right? So in this case, I then have to multiply this guy then by sine of phi to make sure that I'm only looking then in the phi or in the vertical direction. So I only have the vertical component of this force. Good. Next thing is, let's write this in as a magnitude. So this is going to be then equal to the integral of the current times the magnitude of the differential length crossed by then the external magnetic field times sine of the angle phi in the j hat direction. So I've already established the direction is in the vertical direction. So let's go ahead and say that on here. So now what I've done here is I've turned this thing from a cross product into simply a magnitude, which also deals with the cross product. Now let's write out what this thing is by definition. So this thing is then going to be equal to the integral I of then the magnitude of the differential length crossed then by B, which is then the magnitude of the magnetic field, times sine of the angle between them, let's call that guy theta. And then I need the piece that tells me looking at the vertical portion, which is then the sine of phi, all then in the j hat direction. Okay? Okay, let's keep going. What's DL? So DL is simply then again this small differential length here. So this is my DL. So this distance from this point here to this point here. So this thing has a width of it right here, which is my DL. So that's simply my DL. Now, what else? What is then the angle theta between the external magnetic field and that DL? Where that DL again is pointing in the direction of the current, which means my DL at this stage is actually pointing in this direction. So it's the direction of my DL. So what's the angle theta between DL and the external magnetic field in this case? So DL is this way. B is this way. What's the angle between those two things? 90 degrees, right? So in this case, theta is simply equal to 90 degrees, or what side of 90? Which one? Good. So this thing is going to simplify then to that the total magnetic field is going to be equal to the integral of the current times then dl times b times c sine of phi all in the j hat direction.
Why do we get rid of the magnitude?
Because now when I'm just writing it out as a vector, I'm implying that's a magnitude. So here when I'm just writing DL, I'm being lazy, and this is the same thing as this. I just don't want to write that. Now what? Well, what's DL? Let's go back to our picture. DL again is this length of here, but again, if I draw a line from here to this, draw a line from here to this, what I know is that this side has a constant radius of r, this side has a constant radius of r, which means I can rewrite DL here in terms of arc length. So that this thing has a differential angle, let's call that then dt. So let me kind of blow this thing up over here. So you can kind of see what I'm doing here. So let's do a blown up version. So this is my DL. My DL. In this case, I'm going to extend this guy back to the origin, extend this guy here to the origin, so that this has the side length of r, this has the side length of r. But I'm cutting out this little wedge here. This little wedge has a differential width, which is my differential angle of d phi. So in this case, I can use arc length to then rewrite dl in terms of r and d phi, and then simply r d phi. Okay? Let's plug that back in. So finally, this is going to become equal to then the integral of the current times r d phi times the magnetic field times sine of the angle, all in the j hat direction. Now, in this case, what I know is I is a constant, r is a constant, b is a constant. I can factor all those out. J is also a constant. I can pull that out. So this thing finally is going to become the current times the radius times the magnetic field integral sine of phi d phi, all in the j hat direction. Okay. Finally, I just need my bounds of integration. My bounds of integration is, well, I'm integrating over a semicircle, which means I'm going to integrate this guy from 0 to pi. Or from pi to 0, but let's go 0 to pi. I'm going to integrate this guy from 0 to pi. Actually, let's go with pi to 0. That's what it takes. Go pi to 0. Because we're going counterclockwise in this case. Pi to 0. Make me feel better about my life. Okay. Always okay? What is the integral of sine theta? Minus cosine, so this is going to become the same thing as negative RB. Then I have a cosine of phi evaluated from phi is equal to pi to phi is equal to 0. All in the j hat direction. So finally, this thing is going to become equal to what? Twice of the current times R times B in the j hat direction. In this case, I actually ended up dropping the negative because I know it has to point in the positive y direction. If I kept that negative, then I would end up in the negative j direction, which is not true. So in this case, what I end up doing is I end up taking a magnitude moment. Because again, we already established that the actual direction has to be in a positive y direction. So if I have that negative sign on the inside, that's going to force it to go in the negative j direction, but that's just not true. It's point in positive y direction. It's okay? Right, so when I put this in here, I get a cosine of 0, which is 1, minus a minus 1, which is then 2, so that's where this portion comes from. Okay? So this is our overall net force on this wire. So all of it comes down to simply the circular portion of the wire. What's up over?
Still would be a thing where the magnetic field is not constant.
So if the magnetic field is not constant, I would have to know how it changes going from one side of the wire to the other side. So in this case, what would happen is if the magnetic field was not constant, I would need to know it, hopefully, as a function of phi. If it wasn't, it would be a little more complicated. In that case, actually, it would be a lot more complicated.
So even if it's a function of c, would it still only have a j hat direction?
Well, that depends on how it changed. That depends on how it changed. So if it did something like simply a sine or a cosine, let's see here. Good question. So if it was a sine curve, it would still only be in the vertical direction. But if it was a cosine curve, in that case, that would be really weird because what that would be saying is that on this side, the current is going this way, but on this side, the current would be going this way. So there has to be some sort of source of magnetic or of a current here to drive the current in two different directions. But in that case, then yeah, what would happen is it was going into two different directions. In one case, the force would be inward, and the other case, the force would be outward, which means the vertical portions of the force would cancel. Actually, in that case, one's going this way, one's going this way. Actually, everything would cancel. There'd be actually no force on it in that case. But yeah, it depends on how it's actually changing in that case to completely say. Okay? There.
We have a non-constant b with how it changes.
Yes. Yeah. You would have to be told how it is actually changing. And in this class, it would have to come down to a single integral. So it would have to be changing in this case as a function of theta, or a function of phi in this case. In a more advanced class, in a more general sense, it could be changing not only how the angle is changing, but also how the height is changing as well. So basically changing both the x direction and y direction independently. In that case, then you couldn't rewrite dl in terms of simply r d phi. You would have to write it in terms of dx and then dy, and then do actually a double integral in that case instead of a single integral. But that's a whole other story. So we're not going to go. So our next topic, if we get there, is then, so we know is that now this current carrying wire now feels a force, but remember what actually creates current is single individual charged particles which are moving. Which means that this thing is actually feeling a force because each one of the charged particles inside of it actually is going to feel a force. We now want to know what is the force on each one of these individual charged particles. So we want to know then what is the force on a single charged particle. So this is what we want to know. So just to illustrate it a little bit more, here's my wire. Okay, so here's my wire. Let's say I have a straight wire carrying current. So here's my current. Again, in some sort of external magnetic field. So this is my external magnetic field. Now, on the inside of the wire, what we know is we actually have individual charge carriers. So here's my individual charge carriers, which have a velocity, which is what we call the drift velocity, which is then moving in the direction of the current. Okay. Cool. So let's start off again with our force. We know our force on the wire is equal then to what? The current times the length crossed then by the external magnetic field. Now let's think about current. We know current, though, is equal to what? The change in charge divided by the change in time. Now in this case, we're looking at the amount of charges which pass from this side of the wire to this side of the wire, which means then that what? The total amount of charge then is simply going to be the total number of charges which pass through times the charge of each one of these, which is simply Q, divided by that total amount of time. So in this case, it's going to be equal to the total number of charges N times the charge of each charge, which is Q, divided by the total time of delta T. What's the length? Well, I know the length that this particle starts off here, ends up over here, but since they're moving with a constant velocity of v, what I also know then is that this total length that this thing has traveled, going from this side to this side, is then going to be equal to simply the velocity at which they're moving times then the change in time. So if I looked at one single charge that moved from this location to this location over this time frame of delta t, then the length at which it travels is then going to be by our second kinematic equation, simply equal to the velocity times the change in time because it has no acceleration. Let's now use those two things into this expression here. So let's do that. So this is now going to become equal to the charge, which is the number of charges times the charge divided by the change in time, times the length, which is then the velocity, times the change in time, crossed then by the external magnetic field. What happens with this change in time here and this change in time here? They cancel because it's the same time frame. So this is then going to be equal to then the number of charges times the charge times the velocity then crossed by the external magnetic field. But this is the total force on all n number of those particles, which means the total force on one single particle is simply this entire thing without being. So from this, what we then learn is that the force on a single charge particle moving in an external magnetic field is then equal to the charge of that charged particle times its velocity crossed then by the external magnetic field. So this is then the force on a single charged particle. Everyone's okay?
Can you go back a second?
I would love to. Here. Okay, so this delta T cancels that. Okay. And again, here we're dropping the n because this is the total force on all n number of those particles, but I want to know on a single charge particle, which means it's everything except for that n. So this is the charge or the force on a single charge particle moving in an external magnetic field. So what does this thing tell me? This thing tells me that to what? Experience a force, a particle has to have a charge, which means if I had a neutron moving in an external magnetic field, it would feel no force. It has no charge, therefore it feels no force. Nothing happens to it. There has to be a charged particle. Has to have a velocity, which means if I had a single charge particle sitting stationary in an external magnetic field, it also feels no force because it's not moving. And it also has to have a velocity somehow perpendicular to the magnetic field because the velocity is parallel or anti-parallel to the magnetic field. It also feels no force because the sine of the angle would either be 0 or 180 degrees. Sine of 0, 180 degrees is simply equal to 0. So it has to be somehow moving perpendicular to a magnetic field to actually experience force. These are three things that have to be present. So the three things are, number one, has to have a charge. Two, has to have a velocity. And number three, V must be somehow perpendicular to the magnetic field. Means it doesn't have to be totally perpendicular, but there has to be a component which is perpendicular to the magnetic field. Otherwise, this thing feels no force. Always okay? Let's do an example. So this says we have an electron, which is traveling at a rate of 2 × 10⁷ meters per second in a plane perpendicular to a uniform 0.01 Tesla external magnetic field. So what we want to do then is describe the path of this electron. That's what we want to do. What is the electron going to do? What's it going to do? So let's draw our scenario here. So in this case, we have a charge. Here's my single charge. We know the charge in this case is simply an electron, so the charge is equal to a negative. And let's say at this moment, it's moving to the right with a velocity of v, or the magnitude of that velocity was equal to 2 × 10⁷ meters per second. And this thing is in an external magnetic field, which is perpendicular to that, which means it's going to be either into the board or out of the board. So which way you want it to go? Into the board or out of the board? Into the board. Great. So in this case, we know we have magnetic field everywhere. We know the magnitude of this magnetic field is equal to 0.01 Tesla by magnetic field strength. So from here, we want to describe what is this particle going to do. So first, let's use our right-hand rule. What's this thing going to do? So in this case, again, we point our fingers in the direction of the velocity, curl towards the external magnetic field, which means I have to rotate my palm towards the external magnetic field, curl my fingers inward, which means my force would be upward. But what's the sign of the charge of an electron? Negative, which means if I have a negative charge, what do I have to do to the direction of my force? Rotate by 180 degrees, because that negative sign flips it by 180 degrees based off what we talked about before in 205. So in this case, if it was a positive charge particle, the force would be in this direction. But since it's a negative charge particle, that extra negative has to rotate it downward, which means in this case, this is going to feel a force in this direction. It's going to be my magnetic force. Okay? So what's this thing going to do? It's trying to move this way in a straight line, but this force is acting on it in this direction, which means if there's a force on it, there's also an acceleration on it, which means the acceleration is going to cause it to curve down. So this thing is going to start to move down. So that means at some later point, this thing is going to start to curve down and then get to this point. What happens at this point? Well, at this point, the velocity is tangential to the direction it's going. So this is my velocity vector. So in this case, I point my fingers in the direction of the velocity this way. Curl towards the external magnetic field, so rotate my palm again in the direction of the magnetic field. Curl towards the magnetic field, which means it should point out that direction. But since it's a negative charge, I have to rotate by 180 degrees, which means at this point, my force is then going to point in this direction. It's going to keep moving, so it's going to keep being pulled. So it's going to move down to this location over here. Let's say now it's here. So at this point, the velocity is then pointing in this direction. So it's my velocity v. So what's the direction of the force? At this point, again, I put my fingers down in the direction of the velocity, curl towards the external magnetic field, which would be into the board. So my thumb would point away from this. But again, it's a negative charge. I got to rotate by an extra 180 degrees, which means this thing then is going to point in this direction. And it's okay. Now, if I keep following this pattern, what type of path is this thing going to be? A circle. So what's going to happen is this thing is actually going to end up creating a circle, where the circle then has a radius of r. Which means, what type of motion is my charged particle undergoing? What's happening to the size of the velocity? Is it changing? Is the size of the velocity, i.e. the speed, is the speed ever changing? Yes or no? No, and why?
Because the forces are canceling.
Because the force is always perpendicular to the direction of the velocity, which means what type of acceleration do I have on this thing? I have a centripetal acceleration. So what I know is here I have a centripetal acceleration pulling it towards the center. And since the speed never changes, I have a centripetal acceleration. That means that the path this thing undergoes is then uniform circular motion. This thing is simply going to sweep out a circle, constant velocity, a radius of r. This thing is simply going to do this. That's it. So whenever my velocity is purely perpendicular to the direction of the magnetic field, this thing is going to undergo a circle. That's it. This thing has a constant radius of r, and it has a constant velocity because, again, the force is always perpendicular to the direction of the speed. So we want to know then, what then is the radius of the circle that this thing undergoes? So let's look at the radius. So to find a radius, in this case, I would then say, by Newton's second law, the sum of the forces acting on my charged particle must then be equal to the mass times the acceleration, but in this case, this is going to be the centripetal acceleration. Now, in this case, the force is in the direction of the centripetal acceleration. So I'm just going to write this then as the sum of the forces is equal to MAC. The only force acting on this thing is then the magnetic force. That's what's causing it to move in a circle. So I then get the magnetic force then is equal to mv squared over r. Remember, centripetal acceleration by its definition is the velocity squared divided by the radius. Okay? Here, my magnetic force we now know is going to be equal to the charge, which in this case we know is the fundamental charge, times the mass times the. So the charge times the velocity times the external magnetic field times sine of the angle between the two is equal then to the mass times the velocity squared divided by the radius. In this case, what's the angle between the velocity and the magnetic field? So my velocity is always in this plane. My magnetic field is always perpendicular to that plane. So what's the angle between the two? 90. So in this case, I know that theta is equal to 90 degrees. So I'm going to get the charge times the velocity times the magnetic field is then equal to the mass times the velocity squared divided by the radius. Blast you. This velocity cancels this one. And then from here, I can finally solve for the radius. So this tells me that my radius then is going to be equal to mass times velocity divided by the charge times the magnetic field. So this is the radius at which this thing sweeps out. For our case, we plug in our numbers. In this case, we find the radius then equals to 1.1 times 10 to the minus 2 meters, which means this thing sweeps out a radius of 1.1 centimeters for our electron. Okay. Now, what would happen if it's not fully perpendicular? If it was not fully perpendicular, so not fully perpendicular to B, what happened in this case is you would actually create a helix. You get a helical shape. So what would happen in this case then is, let's say that my magnetic field, for example, points this direction. And let's say my velocity pointed in this direction. So what happened in this case then is that the parallel piece of the velocity would only cause a drift. So what happened is the parallel piece of the velocity would only cause it to keep moving in this direction. That's it. The perpendicular piece of the velocity, draw that in blue, would cause it to actually move in a circle. So what would end up happening then is that this charged particle would end up then just going like this. So it would actually create a helix. So if I was looking down the direction of the magnetic field, it would be creating a circle with a fixed radius, where that radius would then be determined by the perpendicular piece of the velocity. The parallel piece would only just cause it to keep moving along the direction of the magnetic field. Okay. What else do we know? We know that this thing also has a period. Let's talk about the period. Since it moves under uniform circular motion, it has to have a period. So if this is my circle, we know what? The time it takes to go around through the circle is what we call the period. The distance this thing is going to travel is then going to be pi times r, which means by our second kinematic equation, we're going to get 2 pi times r is then equal to the velocity times the period, which means our period then is going to be equal to 2 pi r divided by the speed. But from our previous page, we also know that the radius is the same thing as the mass times velocity divided by the charge times the magnetic field. So this thing is then going to become, let me write it on the next slide. So we're going to get 2 pi divided by the speed times, this was the mass times the speed divided by the charge times the magnetic field, which means the velocities are going to cancel. So this thing is going to become then equal to 2 pi times the mass divided by the charge times the magnetic field. So this is the period of oscillation. But we also know this thing has a frequency. That frequency then is equal to 1 over the period. So it's going to be equal to the charge times the magnetic field divided by twice the mass. This is then the frequency. This particular frequency has a special name. This is what's called cyclotron frequency. So the cyclotron frequency, in this case, is simply dictated by the charge and the mass and the external magnetic field, not how fast the object is actually going. So tomorrow we'll look at some more examples of this, see how this thing works, especially in nature. So this actually leads to a lot of also interesting type things. Mass spectrometers is one of them. So this is actually completely how you determine the mass spectrometer. The aurora borealis is actually based off of this as well. So the pretty northern lights is all of this. I'll talk about how that actually works. And then this also led to the discovery of the electron, which we'll also talk about. So how all this stuff kind of incorporates into these different things. We're going to talk a lot of chemistry tomorrow. Oh, so basically, if I now go to think of the war, I'm going to go here. You made us the direction. Rowan asked, what is the path at which the particle undergoes? So because by getting my right hand.
Yeah. By the way, if we go out further, to come to, I don't know if we're
It's
right.
always perpendicular.
Well, Cindy,
That's-
why did you know?
No, so all it is a charged particle moving perpendicular to the magnetic. So it has nothing to do with the water. So this is just the overall path that was.
So charged particles always move in a circle.
Always move in a circle as long as there's a piece of the velocity perpendicular to the magnetic field. Again, if it's not completely perpendicular, what happens is you create a helix inside. Okay.
Hi, I won't be here tomorrow. We were recording.
Yeah, because I got somebody out. They had a surgery, so
Okay.
I'm recording this for that. As far as I know, it's only going to happen through Monday.
Okay, that's fine. I'll just.
Hopefully after Monday, I won't have to record anymore.
Okay. And then I have a question.
Sure.
So when we saw for FB, is that different than B? Because there was one equation that we knew FB, but we were solving for B. But I thought we were referring to it as like the same name.
Well, somewhat. So remember, so that's going way back to. So that was this problem. So basically, the B comes in from the FB. So we have is that FB is equal to IL cross B.
Yeah.
So in this case, we knew what FB was. That was this thing. We knew what the length was. We also knew what the magnitude of the current was. So in that case, we know everything except for B.
Okay.
So in this case, we were kind of solving a little bit backwards. We knew this, 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 and this. So now we wanted to find this.
What did the question say? Because I guess I get tripped up on like what's the
Oh, got
what
it.
did the question say? Because the magnitude, or I guess what's the name for FB and what's the name for B? Because I get tripped up.
Okay,
like, on
so
the text.
FB is simply the force.
Okay.
So let's go back to the question.
And then would B be the magnitude
Of the magnetic field, correct.
Okay.
So in this case, we're told that, and we know F, so this is actually F sub B. So in this case, we're told that it's determined to have a magnitude, so in this case, talking about the force. So it has a downward force that's determined to have a magnitude of this. So that is FB.
Okay.
And then the question itself then said, what is the magnitude of the magnetic field?
So then that would be.
So that would be B. Yeah.
Okay.
So B is explicitly the magnetic field itself. And then FB in this case is the force generated by that magnetic field.
Okay.
So that's mostly just to distinguish it from the other forces that we've seen before, for example. So FE, we said before, was the force on a charged particle by an electric field. We now know FB, which is the magnetic field the force by the magnetic field, right? So we could write all these different ones. So basically I'm just writing F of E to distinguish that this is an electric force.
Okay.
And then write this one as F of B, so this is a magnetic force. So I could do the same thing with other things as well. Like for example, I could call the normal force F sub N. Right, tension force, I could call it F sub T, things like that. So that way I'm just distinguishing what the force actually is.
All right, that makes sense. Thank you.
You're welcome.